theorem, with the application of Buckingham pi theorem, the objective is to is to form dimensionless group, right? Out of this, for example, in this case, the pressure drop is a function of dimension d1, d2, velocity, viscosity, and rho. How to form dimensionless group out of these variables? Now you find that there are 6 variables in this case, right? 1, 2, 3, 4, 5, 6. So n is equals to 6. And the number of basic dimension it involves, you have n, l, and t, right, in the variables. So n is equals to 3. So it's 6 minus 3 got 3 pi groups, right? So now in this application of Buckingham pi theorem, now it is important that you know the basic dimension. Right? The basic dimension, it can be m, l, and t, which is a mass, length, time system, or the force, length, and time. Now you can use either one. You will still arrive at the same dimensionless group eventually. So in the last questions, I will use the FLT system, right, force, length, time system. Okay, now let us take a look at the 3 pi groups, right? So we have pi group 1, pi group 2, pi group 3. Now these are the 3 groups, right? We call it pi group. Now we want to make this group dimensionless. So we have we need to have some form of repeating variables. Now repeating variables for academic reasons, repeating variables for exams will always be given. Most of the time will be given. Now otherwise you will have to select the repeating variables yourself. Now there will be a guide to tell you how we can select the repeating variables. Okay. Now in this case, the repeating variables are given rho, v, and d. Well, one of the reasons is that now we feel that rho, v, and d is important, and we want these 3 terms, rho, v, and d, to be represented in the first pi group, in the second pi group, and also in the third pi group. All right. So we have rho, v, and d in the second pi group, rho, v, and d in the third pi group. Right. Now in each of these repeating variables, we raise these variables to a constant a, b, and c, all right. And then you fill in the remaining variables that are not selected, and you start with pressure drop, viscosity, and diameter 2, right? Diameter 2. Okay, now then you will have to put in the basic dimensions, right? For the basic dimension of delta pressure drop, right? M L over T squared, and then followed by the basic dimension of density, velocity, and diameter, right? So this is raised to the power A, B, and C. Okay? For second pi group and the third pi group. Okay. Now you have to solve for A, B, and C so that the M, L, and T of this whole group, right? This whole group all becomes raised to the power 0, which means that they're all dimensionless, right? They're dimensionless. So now if you solve for A, B, and C such that the M, L, and T, they're all raised to the power 0, it means that the term pi group 1, pi group 2, there's no dimension at all. Okay, now solving this, you find that you arrive at 3 pi groups, right? So these terms are dimensionless. D2 over D1 is dimensionless. It's pretty obvious. Now this is Reynolds number is dimensionless. Okay. Now let's go through one exercise, right? Just to recap how we obtain pi group 1. How do we make pi group 1 to be dimensionless? So we take first pi group. This is pi group 1. Okay, and then fill in the dimensionless term. Now we want to make this whole pi group to be dimensionless. So what it means is that the M, L, and T should be 0. So what should be the value of A, B, and C? So what should be the value of B? Now in order to make this term M, right, raised to the power raised to the power 0. Think about that. B has to be minus 1, right? So B has to be minus 1. Look at this term here. This is M raised to the power 1. So what should B be? B has to be minus 1. So now when B is minus 1, that means this whole term is inverted. So it becomes L cubed over M. So these two terms cancel out. So you have M raised to the power 0. Now next, how to make this term T raised to the power 0? You have to make sure that A is equals to minus 2. So when A is minus 2, this term is inverted. So therefore, the T term, right? So this is T squared and T squared is cancelled out. So you have T to the power 0. Now lastly, you want to make L, the length representation to be raised to the power 0. So C has to be 0. So this will give you the first pi group, that is the dimensionless term. White is the first pi group. Now similarly for second pi group, how to make M naught equals 0? You're going to put B equals minus 1. Right, and this term M and this term M will cancel out. Right? And then how to make this term T is equals to how to make this term T equals to 0, you're going to make A equals minus 1, and then lastly you put C equals minus 1, and then you get this term, the length term will cancel out. So eventually you have the second pi group, right? So you go through this process of eliminating M, L, and T, alright, make sure that they're always to power 0. So then you will arrive at the second pi group, which is dimensionless. You can write this term like this, or you can written as rho, v, over mu, which is this is the Reynolds number, right? So this commonly known as Reynolds number. So you can either write mu over rho, v, or any commonly you use rho, v, over Reynolds number. So similarly, you do this for pi group 3, right? Okay, now this is some guide as to how we can use, how we can select the repeating variables. Okay, so we divide these repeating variables into categories such as the geometry of the object, the property of the fluid that's involved, and some form of an external force, right, that is applied in this case. So now, geometry objects, we have, for example, the length of the object, the height, the width, the diameter, and then how rough is the maybe the surface roughness. So these are this will be classified as a geometry, right? Some form of dimension in it. Now the properties will be mainly in fluid mechanics, the properties that is of important will be the density of the fluid and the viscosity of the fluid, right? It's mainly these two. And then finally, what is external force? External force is something that drives the flow, right? It drives the flow. So velocity is associated with external force because you need a force in order to drive the flow, in order to have some form of velocity. And then so is pressure, force, acceleration. So these are classified under the force. So now, if we have a problem, say pressure drop is a function of velocity, density, viscosity, diameter, and some form of the roughness of the pipe. Now, if we want to form repeating variables, then we can choose this, right? This combination, right? So you say without looking at this tree, I can choose this combination, any tree. Now, the reason why this is not going to be a good set of repeating variable is that now you have density and viscosity, right, in this group, and both density and viscosity comes from the same group of property. So it's not going to be a good repeating variable, right? And then so is this term, diameter and the roughness. It comes from the same category. It's not likely to be a good set of repeating variable. And probably this one is because you have one from each, right? One from each of the category, okay? And this is not likely to be good because you have two, diameter and roughness from the same category. You have a density and mu from the same category. And then the last group, maybe V, rho, mu. So you have one from each category. So what it means is that now if you select the repeating variable, now this is okay, this is also okay. And then you would end up with two sets of dimensionless group, right? You're not wrong, right? You're not wrong. So which means that we do not have a unique solution for when it comes to dimensionless group. Okay, so we have to explore and then experimental investigation has to be carried out to see which one would be the most suitable set of dimensionless term. Okay, now let's take a look at question number 1. Right, go to question number 1. Consider a uniform stream of fluid flow around a cylinder. The drag force, right? The drag force, right? Fluid flow around a cylinder. The drag force on the cylinder depends on the velocity, the density, the viscosity, the diameter, and the length of the cylinder. Right? Now you're asked to derive suitable pi group or dimensionless term and a general relationship for the drag force. Now, if the repeating variable are rho, v, and d, right? So repeating variables are given. So we go through the same exercise, right? The approach to develop dimensionless term is, I think, is pretty systematic. First, you must know the basic dimension. Now, as I say, you can use mass length time system or the force length time system, right? So then you need to know how you're going to get around from Newton into mass length at a time, right? So there's an approach to it. You go through the lecture notes again. So in this case, Newton is not this is a force, right? So you have to convert this into mass length and time, but basically force, right? F equals to ma. So you go from there. Now mass, this is velocity, length per time, density, viscosity, and then in this case you have diameter or length, right? Diameter or length, which the unit is meter, so we have a representation of length, right? System going to use length. There are 6 variables, right? There are 6 variables, and you have m, l, and t are involved. So m equals to 3. So hence you have 3 pi groups. You have 3 pi groups, right? So we're going to put these repeating variables into the 3 pi groups, right? 3 pi groups, repeating variables, and we're going to put it all into 3 groups. So we are going to develop 3-dimensionless group or 3 pi group. This is repeating variable. Okay, and we're going to raise to the power ABC to these repeating variables. And then remaining variables that are not used in the repeating variables, we're going to put them one at a time in the dimensionless group. Okay. So what you can see here is that now you have all the variables, right, from drag force, velocity, density, viscosity, diameter, and length. They are all represented in the 3-dimensionless group that we want to develop, right? They are all represented. Now, ABC are constants, and then we want to develop pi group 1, 2, 3 such that these 3 groups are dimensionless. So solve for one group at a time, right? You take one group at a time. So how to make each group dimensionless? We have went through this in the review lectures, right? So we take pi group 1 for example, we're going to solve for this. So you're going to fill in, right? You're going to fill in all the basic dimensions into this first pi group, and to make sure that solve A, B, and C such that M, L, and T, they're all raised to the power 0. So look at this term first. So you fill in all the M, L, and T's into the system. Okay. This group, and this group comes from here. That comes from here. Okay. How to make this dimensionless? What should the values of A, B, and C? So to eliminate the M, when make M equals raised to the power 0, B has to be minus 1. Right? B has to be minus 1. So this term and this term cancel out. So to what to eliminate next? So you can think. Now if you want to raise t to the power 0, now should you raise t to the power 0 first or you put L to the power 0 first? Right? So here you have a choice. Now you notice that now this term is already out. And then you have length raised to the power 3. So we have length raised to the power 3 and what about this one? Length raised to the power A and then length raised to the power C. So now you cannot eliminate L because you have two unknowns here, the two unknowns A and C. But you can eliminate T because you have only one unknown. A is unknown. There is no T involved, right? No time involved in this case, right? Over this side. So eliminate T. A has to be minus 2. A has to be minus 2. And these two terms cancel out. All right. Okay. Equating. Lastly, you equate the L, right? Or eliminate L. Then you find this new term. Okay. So you got to fill in, all right? So A, B, and C, they're all known, right? So you got to fill in all this term. Okay. Hence you develop the first pi group. All right. Okay, similarly for pi group 2, all right, so I'll go through very fast. So the approach to develop dimensionless group is pretty systematic, okay? So for A, B, and C, eliminate M, so we can count B has to be minus 1. Eliminate T, A has to be minus 1. And you have the second pi group. So we can write mu over rho Vd is dimensionless, or more commonly, you invert it, rho Vd over mu, that's Reynolds number. You should use that. Okay. So similarly for pi group 3, right, the third pi group, you find that the third pi group, if you look at this, right, this is L, length. So I think there is no mass and time involved. So you only have this term, right? So by inspection straight away, you can actually write this is the third pi group, L divided by, right, this has to be 0, this has 0, you can only divide it by this term D, right? So this is dimensionless. Now you can write L over D or D over L. So there are 3 pi groups, right? You can write this. The first pi group, right, so the drag force is a function of Reynolds number and the length to diameter ratio or diameter to length ratio. Okay? So this is a drag force coefficient, right, it's dimensionless, Reynolds number, and lastly, the diameter to length ratio. Okay, now question number 2, again, we have another, this is a second question relating to develop a dimensionless group, right? So the pressure drop, right, pressure drop it depends on diameter, the omega, rho, and Q. Okay, determine suitable dimensionless group. Here we have 5. N is 5. Right, then you write down the basic dimension that involved. N is 3. So hence you have 2 pi groups. Right, you have 2 pi groups. Okay, now I'm going to use the d omega rho as repeating variables. So 2 pi groups, pi group 1 and pi group 2. Okay, d omega rho as repeating variable. First group, second group. This is the remaining variables that are not used. Then you raise this to the power A, B, and C. Okay. Raise the repeating variables to the power A, B, and C. So now the objective is to make this whole term dimensionless, right? So we solve for A, B, and C. Okay. So this is the approach to solve for dimensionless group is pretty systematic. Now it's important that you know the basic dimension. Now we can use either ML or T, or FLT or FLT, force length time system. Okay. So in the last question, question number 4, I will use the force length time system. Okay. So you have 2 pi groups. Okay, now in these questions, first we have to develop the relationship, right? You have a pressure drop, but you take note, this is pressure drop per unit length, right? It's different, right? It's different pressure drop. So the pressure drop per unit length, so it means that this pressure drop per length now is is considered as one variable, right? So this pressure drop per unit length, it depends on the flow rate, the diameter, and the viscosity of the fluid. And then you have these experimental data that are given. But first, let us develop the general relationship first. Now, what's the meaning of this general relationship? And eventually I will explain what is this for the specific application. Okay, now we apply the Buckingham pi theorem to find the dimensionless term. Okay, n equals 4, there are 4 variables, right? Delta P over rho is considered as 1. Okay, now delta P over rho is you take note, right? This is per unit length, right? So, but for pressure drop is mass per length t squared, right? So, it is different, right? So, you have another term here, length. So, pressure drop per unit length, the MLT system is different from pressure drop, right? So, take note, this is a common mistake. Okay, now there's only one pi group, okay? So, we're going to use this as the, this will become the repeating variables, right? So, and then you go through the process of eliminating the ML and T. So, you find that you have one dimensionless term and solving ABC, right? So, this is a dimensionless group. Now, the second part of it is actually the application. Now, to derive a general relationship, how are you going to do this with the given experimental data? Okay, now, this term, right? So you take note. Now, this term is dimensionless, right? There's no dimensionless. So it's a unit with no, it's an index, right? There's no dimension to it. So this is dimensionless. It's a constant, the constant that we found. It's a given experimental data. Now, the diameter is small, right? The given diameter is 2 mm, and then the length of between the pressure drop measurement is 300 mm, and the viscosity is 0.004. Okay. Now, this is the experimental data that were derived, right? So the flow through a very small pipe, 2 mm diameter, now at 3.36 times 10 to the power minus 6 meter cube per second, the measured pressure drop is 1.1 times 10 to the power 4. Now this pressure drop is measured across the distance of 300 ml. 300 ml, okay? So take a look at this. Now, this term, now if you substitute the value of the flow pressure drop, the flow rate, the viscosity, the length, and the diameter, you will have arrived at the number 40.6. Okay, so this is the value, right? The value of the first of this pi, right? The pi. So it's a constant. So this becomes a constant, 40.6. First pi group, 40.6. Now, if you substitute the value of 4.9, the corresponding pressure drop becomes higher, and it yield 40.7. Okay, and then the next one. So at a higher flow rate or greater pressure drop, it is 1.9. The constant is 40.1. So at a higher flow, next higher flow rate, 2.4, the pressure drop, so you yield pi group 1, and then the next higher flow rate. So you'll notice that now as you increase the pressure drop, right? As you increase the pressure drop, the corresponding flow rate becomes higher and higher. Or on the other hand, you can say that now when you increase the flow, increase the flow rate, the pressure drop between the 2 points, right? With the pressure drop between these 2 points, which is placed 300 mm apart, the pressure drop becomes higher and higher and higher. But still, this is the dimensionless constant, right? Dimensional constant, which is about 40.6, 40.5. So this is the constant, it's equals to 40.5, all right? So this is the general relationship, right? So what it means is that now, by measuring the pressure drop between 2 points, right, the flow rate can be predicted, right? The flow rate can be predicted. So look at the system. If you have a pipe diameter that is 2 millimeter, and you have a pressure measurement across that pipe, which is 300 mm apart, and the fluid that you're using is 0.004 Newton second per meter squared, right? This fixed viscosity. So by simply measuring the pressure drop, you can actually predict the flow rate. Okay? Now, how do we do that? How is it possible? Let us take a look at it. Now, first, let us see how this experimental data were obtained, right? We see how this experimental data were obtained first. Now, there is an experimental setup. The experimental setup comprises of a diameter that is 2 millimeter, and the viscosity of the fluid that we are going to test is 0.004 Newton second per meter squared, right? So we create the flow, right? So we have a flow that goes through this pipe. Then you measure the volume flow rate. So by measuring the volume and the time taken, you can measure the volume flow rate, right? You can measure the volume flow rate. But at the same time, you also want to measure the pressure drop for this particular flow rate. So for this particular flow rate of 3.6 10 to the power minus 6 meter cube per second, the corresponding pressure drop is 1.1, right? The corresponding pressure drop is 1.1. So next, you increase the flow rate, and then you measure the pressure drop. So you can increase the flow rate, and you measure the corresponding pressure drop. Increase the flow rate, you measure the pressure drop. Increase the flow rate again, you measure the pressure drop. Increase the flow rate, and you measure pressure drop. Okay? Now, so what you have is some kind of a calibration data, right? And you see this calibration data. So increasing the flow rate, a series of pressure flow rate, a series of flow rate, then you measure the pressure. So what is this for? What is this particular experiment and this setup, this arrangement? What is it for? It is for calibration of a device, right? You want to set up, you want to make an experimental device to measure flow rate, and you're measuring the flow in a very small diameter pipe, right, 2 millimeter, which otherwise is very difficult to have a standard flow measuring device such as orifice meter, the nozzle, right? Those are very difficult. So by simply measuring the pressure drop, it is possible that you predict the flow rate. This is the aim. Okay, so this is the calibration data. From this calibration data, you have this term here, 40.5, and this is the dimensionless constant that we derive using dimensional analysis approach. Okay, now the aim is to predict the flow rate by simply measuring the pressure drop, right? Simply the pressure drop P1 and P2, and you take note, the pressure drop P1 and P2, right? P1 minus P2 is placed at a certain distance, right? 0.3 meter apart. Okay, so this experimental setup with respect to this age, they all becomes a fixed parameter. Okay, now let us see how this how flow is being predicted, right? How do we predict the flow from this experimental setup? Okay, now if you rearrange this term, you have flow rate, and then this is delta T over L, this is D4, and then there will be 40.5, and then mu. Now the density of this fluid is 0.004, right? Okay, so you can substitute all this value, so Q becomes, right, 3.2922 times 10 to the power minus 10, right? Then you have this term pressure drop. So if you substitute the value of the pressure drop, then you for this arrangement, you can find the flow rate. You can find the flow rate. Now, you take note that this is only valid for now when you have a viscosity of 0.04, the pipe diameter is 2 millimeter, and the distance apart is 300 meter. Because from this experimental setup, you develop this empirical equation, right? Empirical formula. Okay, now let us check this empirical formula with the given data, right? We check this empirical formula with given data. So this is the data that we have, right? Now, the question that I'm going to ask eventually is now, can the same empirical formula be used to predict the flow rate in the same experimental setup that has a different viscosity, right? So this actually is a question that comes last, okay? So but let us take a look at it. This is flow rate, this is empirical formula. Okay. Now, if you substitute the pressure drop of 1.1 times 10 to the power 4 into this equation, what will you arrive at? You get 3.6214, which is pretty close. So what it means is that you can substitute any value of pressure drop, right? You can substitute 3.0 times 10 to the power 4, you get approximately 9.8. Or you can substitute the value of 3.5 or 2.0, 2.2, right? So any pressure drop that you measure in this system setup, you can use it to predict the flow, okay? But, so the question is, now can you use this empirical formula for the experimental setup with a different viscosity? Now, this is only for viscosity of 0.04, diameter of 2 millimeter, pressure drop 0.3 meters apart, because this formula is derived from this equation with the dimensional analysis approach, alright? So eventually this becomes a specific flow measuring device. What is it specific for? It is specific for measuring flow with viscosity of 0.004, is mu, and in a pipe that is 2 millimeter diameter, and this pressure drop must be measured at 0.3 meters apart. Okay, so it's a very specific flow measuring device. Okay, next. Now let us take a look at the question number 4. Now in these last questions, we also look at that. We're going to focus on its application, right? The application. Now beyond developing dimensionless group, what are we going to do with it? What can we do with it? So here is a very good example of a viscosity meter, right? The concept of measuring viscosity fluid now is shown below here. So what do we have? Now, this is the fluid that we want to measure its corresponding viscosity, right? The fluid is poured into this, the space between. So here I have an outer cylinder, hollow outer cylinder, and then this is an inner solid cylinder, right? Inner solid cylinder. Now, the outer cylinder is rotated by an external means, right? So it may be sitting on the plate and then it's rotating. So when the plate rotates, this outer cylinder will rotate, right? The outer cylinder will rotate freely. But when the outer cylinder rotates, the fluid inside, because of its viscosity, will also rotate. It will also rotate due to the viscous effect of the fluid. It has a tendency to be attached to this outer cylinder. So when the outer cylinder rotates, the inner cylinder will rotate. Now, when the inner cylinder rotates, it will also cause when the fluid here rotates, it will also cause the inner cylinder to rotate. But can the inner cylinder rotate freely? No. The answer is no. In this experimental setup, in the case of viscosity meter, this inner cylinder is held by a fixed support through a spring, right? It's a circular spring, right? Circular spring. Now, when the fluid rotates, it will impart some kind of a force, right? Some kind of force, viscous force, onto the surface of the inner cylinder. So the inner cylinder cannot rotate freely, but it will be twisted. Right? So I use the word twisted. So when this inner cylinder is twisted, it's twisted by the degree or the displacement theta can be measured. So there are two things we measure in this viscosity meter. One, we measure this angle of twist. Second, we want to take note what is the speed, right? The rotating speed of this outer cylinder. So when the outer cylinder rotates, the fluid rotates. When the fluid rotates, you impart a rotating force on the inner cylinder, and the inner cylinder will be twisted. So this angle of twist, what does it depend on? It depends on how fast you twist or how fast you rotate the outer cylinder. It depends on the viscosity of the fluid. It also depends on the spring constant, right? This is a spring constant. If the spring is very steep, then the displacement will be very small. It depends on the diameter, the outer diameter, right? This is the diameter D1 and D2, right? And it also depends on the length, right? It depends on the length of this, or you can say the length or the height from which the fluid is being poured. So when the fluid is being poured into this empty space, now it will always pour up to a fixed level, right? At the fixed level, and this level will remain constant. Every time when you pour, when you want to pass, will always pour up to this level. So this becomes an experimental setup specifically for measuring viscosity of the fluid. Okay, now let us first start to determine what are the sets of dimensionless terms that are suitable in this case. So here you have these variables. Okay, theta depends on all these variables, angle of twist. So we're going to use the force length time system as a basic dimension. Okay. Now previously we used mass length time, but now we're going to use force length time. Now as I said, you can use either one, right? Force length time or mass length time. Right? You both arrive at the same base dimensionless term. Okay, what is this term? Now, this is the angle of twist. Now, does it have any force? There's no force involved in the angle of twist. There's no length involved in the angle of twist. There's no time that is involved in this angle of twist. So the F, L, and T, they are all raised to the power of 0. What about omega? Omega is theta per unit time, or radians per unit time. Right? So there is no dimension in the radians, so you only have per unit time. Viscosity, Newton second per meter squared. So very conveniently, this is force, right? Newton is force, so it's F, time, and then this is per length squared. Now, K is the stiffness constant, force, Newton meter, is the diameter, alright? Okay, diameter D1, D2, and L, you have L, right? The unit meter. Okay, now there are 7 variables, M equals to 3, and then, so therefore you have 4 pi groups, right? 4 pi groups. Okay, now the next step is to select the repeating variable, right? You select the repeating variables. So this is property. Now, omega and K is some kind of a force, it's external force. You need an external force to drive the spring, right? In order to have the spring constant, right? You need the force. Now, omega, you need the force so that it can rotate. And then these 3 terms are geometry. So we'll select one from each. The repeating variable will be one from each of these category. Select one from each category. So how do you select? So I'm going to select mu, K, and L, right? Mu, K, and L. But you can actually select mu, omega, and L. Mu, omega. So this is, you have mu, omega, and L, mu, omega, and D, mu, omega, and D1 or D2, right? Now, if you select this, you're correct. You select this, you are not wrong as well, right? You're not wrong as well, okay? So in this case, we're going to select this. Now, when you select this, now you will have a different, you probably have a different dimensionless term. Okay. So we have 4 dimensionless group. We're going to select mu, K, and L as repeating variable. Right. So the first, this is one of the variables that we have, omega, D1, D2. All right. So I'm going to solve for A, B, and C. I want to solve for A, B, and C so that the A, B, and C are constant, such that the whole term M, L, and T, F, L, and T are always the power of C. Right? So take note of the dimensions, basic dimensions, to fill this in. Theta. Now theta has there has no force, no length, and no time. So therefore, what it means is that the constant A, B, and C, they are all 0. Right? There's no involvement of force, length, and time. So the first pi group, we only have theta. Right? There's only theta. There's the first pi group, right? This first pi group is theta. Look at the second pi group, omega. Omega is 1 over time. Right? This is mu, K, and L. Right? Mu, K, and L. Right? Solving for this, you find that you have A is 1, B is minus 1, and C will be 3. Right? C is 3. So we have a second pi group. So by now you should be familiarized with, you should be quite familiar with solving for A, B, and C, developing the dimensionless term, right? Dimensionless term. So 2 dimensions term, and finally we have the dimension, the third and the fourth. Okay, the third and the fourth. So this by inspection, right? Now this is dimension of time, right? No, sorry, length, right? So there's only one length that's involved. So these two A and B has to be 0. By inspection, it has to be 0. So the third pi group will involve diameter 1 and length. So these become dimensionless group. Similarly for pi group 4. You will have D2, right? Diameter 2 divided by the length. Okay, now we have the 4, right? We have all 4 dimensionless group, right? All the dimensionless group. And then we take a look at the question again and see now what are the terms that are constant and what are the terms that you can actually ignore, that can be ignored. And the important terms. Now, these are the 4 dimensionless group that we have formed. Now, of important that's useful, right? The functional relationship we can obtain, it will be, right? Let us take a note. Now, D1, D2, and L3. Now, these are constants. They are constant. Now, L3 is constant. What it means is that when you pour fluid into the viscosity meter, you always pour it when you reach this length L equals 0.3. So this term is a constant, right? It does not change. This term does not change. So what change will be theta and the second term. Theta and the second term, right? So where this functional relationship, that theta is a function of omega mu L cube over K. Right? So this is a functional relationship. Theta varies with omega mu L cube over K, right? Theta varies with this pi group 2. Okay, now we take a look at the information that we have. So if you take a look at, let's say now, when you rotate the outer cylinder at 0.3 radians per second, the inner cylinder will get twisted by an angle of 0.89 radians, right? Now when you increase the speed of rotation, this angle of twist becomes greater and greater and greater and greater, right? The angle of twist increases as you increase the rotating speed of the outer cylinder. Okay, now let's see how we can form a relationship or understand is how we can make use of this information. Now this is the data that we have, right? This is data, the given data, and then we have developed this relationship, and this is pi group 2. Now the viscosity that we use for calibration, right, is a known viscosity of 0.5 Newton second per meter squared, right? So to start off with, we need a known viscosity to calibrate this viscosity meter. The spring constant that we're going to use is 40 Newton meter, right? So for subsequent viscosity meter that we are going to build, we're going to use the same spring constant, right? Because we're going to use the same results, right? We're going to use the same constant. Now, when you pour fluid into the viscosimeter, we always pour it up to 0.3 meters. So we're going to substitute these values in here. Now what do you get? You get, substitute this value, you find that this pi group 2, right, this term here is approximately 0.00096 omega, right, omega. So I'm going to estimate, right, just for simplicity, estimate that this is very close to 0.001, okay, so it's 10 to the power minus 3 omega. So I'm going to put this into this, I'm going to substitute the value of omega, right? So what I'm going to have here is, this is pi group 2. Now what is pi group 2? So I'm going to substitute now when omega is equals to 0.3. What is this term? What is pi group 2? It will be approximately, right? Because this is we're going to approximate. So this will be 0.3 times 10 to the power minus 3. Okay? So it's this. So we're going to, as we increase the speed, you'll find that pi 2 increases. So this is what we have, right? So let's increase. Now let us plot the variation of theta with pi group 2, right? Which is this whole term. Now some student will ask, so why don't I plot theta with omega? Well, if you plot theta with omega, then you're ignoring the effects of the length and the spring constant as well, right? Okay, so here when you plot theta with omega with respect to mu L cube and T cube, you plot with pi group 2, you're plotting with a dimensionless constant that involves the length, the spring constant, right? The speed as well as the viscosity. Okay. I'm going to plot this. Right? Now put in the proof. Okay. So you plot in, you substitute the values of when pi group 2, right? Mu omega mu L cube K is 0.3 times 10 to the power minus 3. Corresponding theta is 0.89. Right? So you plot this. Right? You plot this, and you find that this is approximately the relationship is linear. It's linear, right? You plot this and you check it out for yourself. The relationship is linear. So what is a gradient? What is a gradient? Now this is something which is eventually becomes very useful, right? What is the gradient in this case? The gradient will be the opposite divided by hypotenuse, which is this column. This is theta divided by this column, which is omega mu L cube over K. Right? Get this relationship. So you find the gradient. You can find the gradient. So the difference in data. So theta, you can take 6.4 minus 0.89, then divided by the horizontal, this will be 2.14 minus 0.3, right? And then remember to multiply 10 to the power minus 3. You find that the gradient is 2.98, 10 to the power 3. That's a gradient. So what it means that this is a gradient. This is a gradient. So theta divided by omega mu L cube, mu L cube. Sorry, I forgot this. There's an L cube here. There's an L cube over here. Over K is this term, right? This is the term. Okay. So this is an important relationship, right? I missed out this L cube. This is a functional relationship, right? For this specific viscosity meter, right? For this specific viscosity meter. And here, this is the relationship that we want, right? So subsequently, we use this relationship to help us to predict what is the value of the viscosity, right? So in this tutorial, we look at dimensionless term. So first, we must know how to develop the dimensionless term. You're going to use the NLP system. They both end up the same dimensionless term, right? The first part of developing the dimensionless term is pretty systematic. But the second part of the dimensional analysis of problem is how are you going to make use of the dimensionless term that you have solved, right? You have developed to apply it, right? Now next week we will continue this application of dimensionless term on modeling, right? Okay, now this is experimental data that we have. Okay. Now the viscosity of this given fluid, right? The viscosity of this fluid, what is it? It was 0.5 Newton second per meter square, right? Okay. Now let us check. Let us check now. Now if we are going to use any of these omega and theta, omega and corresponding theta, will you get back 0.5 Newton second per meter square? Let us check. We use this number. Okay. So I'm going to put I'm going to spin the cylinder to 1.43 radians per second, and then when you measure the displacement, it is 4.2 radian, right? So now with these numbers, will I get 0.5? Right? Viscosity is this 0.525. Well, it's close enough, but not that good, right? Okay, we look at another number. We put at 0.3, for example here. Theta, corresponding theta is 0.89 in 5 mu, 0.52, right? Slightly better. Then you look at this number, we use another value, 0.82, corresponding theta is 2.5. Find this. Okay, well, it's still not good enough, right? So what seems to be the problem? Okay, we actually supposed to use this empirical formula that we developed, and then for prediction, right? For prediction. Okay, like this, 0.52. So we are just about maybe about 5% off, right? 5% off. Okay, so it's still, there's something missing here, right? There's still something missing here. Now, what actually we did previously was that now, we developed this number, right? Now, we use 0.001 rather than this number. So we use we actually approximate, right? So when you approximate, this is where the error comes in. Now, if you're going to use this exact number, 0.00096 and then omega, right? So you find this value here, right? Slightly different. Okay, so you know that previously we used this as 0.001 omega. So now we're going to use the exact value, and then we develop what is the gradient and what is that relationship. Okay, the gradient. Okay, so this is a gradient. Okay, let me see. Let me put this page. So the gradient should be 6.4 divided by 2.05. So you can take the exact value, which is approximately this value. Okay, now this is a new functional relationship. Right, I'm going to show you for this particular arrangement, right? And let me see now. When we start, right? So let me see what's the number. If you use this, the percentage difference of mu is about this is the value of viscosity, right? This term is the viscosity. So when you substitute these values in here, the viscosity is nearly 0.5. The difference is about 0.9%, right? So but anyway, the objective here is to develop a relationship, right? Is to develop a relationship. And where do we start from? We start from developing a dimensionless term, right? Developing a dimensionless term from, okay, end of tutorial. Okay, make sure you branch to the tutorial before end of the day.